here in the University of Trento as a PhD student in reduced dynamic and feasibility theories for specific structure problems. Before I begin, I would like to take a brief moment to thank again my supervisors for the guidance, Professor Davide Vigoni, Luca Deseri, and Professor Massimiliano Fraldi, and all the other collaborators that have been helping me through the project. Thank you. Today's presentation is going to be divided into two main parts. In each one of them, I'm going to talk about a specific structure problem. I will begin with the first one, dealing with the lamination of non-local films. And our contribution to the literature stands in reduced formulation. Reduced formulation are very useful. They can give a better insight of the physical phenomenon and sometimes produce faster algorithms for the solution of these problems. Then I'm going to move on with the second part, where I'll be dealing with a different problem. We'll start by presenting a material that has been crafted in the recent years. It's an hydrocephaly-based material, ceramic, and we have studied it from the mechanical point of view here in Trento. And I will go on presenting a formulation that helped us to study also the fracture phenomenon and the fracture happening when the material is compressed. Okay, so on with the first part. As I said before, our contribution stands in the development of a dimensionally reduced formulation for the treatment of delamination of thin non-local films. So why do we need to treat non-local materials? Well, there is a lot of effort in technology world we're living in to produce excellent and optimized materials. Some of them exhibit a behavior which is not easily treatable with standard local theories. For example, we have the case of materials in which there is a coupling between a mechanical field and an electrical field, and the electrical field is by definition non-local. There is also the case of high integrated structures, for example, airplanes that can show non-local response to certain type of loads. And last but not least, materials with peculiar microstructures. What does it mean that we need a different model? It means that if one has this cantilever beam and doesn't know the microstructure and tries to evaluate the displacement that a force can induce using classical linear elastic property theory, you would find a different value when compared to the actual experiment. So in these cases, there is the need of local theory. All the materials that I've enlisted are sometimes are made of or can be part of laminated structures. For example, airplanes have a lot of laminated structure in them, and OMMs are actually using. There are present works that propose the solution of building lamps by using laminates. So there is a lot in that sense. And so for these non-local laminates, we need a non-local model and to deal with a classical problem that can affect this type of structures, which is delamination. Delamination is a loss of continuity through the thickness of thin elements, and that can cause a high reduction of the performance of the material in terms of strength, in terms of stiffness. So what did we do in order to produce this reduced formulation? Well, we decided to implement the dynamic model. The dynamic theory of continuum mechanics is one of the possible non-local theories available. It has a feature that makes it particularly well suited for fracture problems. The dynamic theory of continuum mechanics, from the physical point of view, imagines the body as a collection of particles that can interact with one another depending on the relative distance. There is a maximum distance at which two particles can can interact. That is called the horizon, and it's the characteristic length for the internal length of the microstructure. The type of connection that two particles can have, I mean the type of forces that they can exert on one another, is expressed through a constitutive relation. There are a lot of constitutive laws that one can impose. The most simple one is the linear elastic that I'm showing here. This is a linear elastic perfectly brittle behavior. The particles interact, and I mean, the more you elongate their relative distance, the more the strength, the force is exerted from one to the other. And okay, so this is from the physical point of view. In terms of equation of motion, since this is a non-local, strongly non-local theory, the equation of motion is in integral, has an integral form, and this is an integral partial differential equation. The differentiation is only with respect to time. There is no differentiation with respect to space. So it means that you can easily and more naturally treat fracture, because for local theories, typically you need to define strain, which is the derivative of the distribution. But here you don't need it. And it seemed quite well suited for this kind of problem. This is the way that you define the strain energy, the kinetic energy, and the work of the external loads. Okay, so this is the procedure that one can implement to linearize the constitutive behavior of the material. Even if you linearize it, you can still retain a nonlinear behavior, since this function over here is the bond breakage function. It tells when the bonds reaches the critical elongation and they break irreversibly. So even since this relation here is vectorial, you linearize it, but you still obtain something that is nonlinear if you keep the breakage function. Okay, so this is just some of the kernels that you can use for the equilibrium equation. And those over there are condition on the stiffness and on the energy that has to be bounded, and stiffness has to be positive there. Okay, so dynamics has been used to deal with thin elements. Reduced formulation have been implemented, but all the reduced formulation treat only tearing and bending. They don't explicitly treat delamination. So this is where our contribution stands. And how did we do that? Well, we made an ansatz on the displacement field. We thought that since the theory is well suited to accept jumps in the displacement field, we could explicitly write the displacement of our body, our thin body, as the sum of two contributions. One is the continuous part, and one is the jump part. From the more mathematical language, we mean that the space in which geometrical changes of the configuration of the body are accepted instead of the function of special bounded variation. Okay, so by making these ansatz and adding assumptions on both the fields, for example, the continuous part is just expanded through thickness. The thickness is assumed to be small, so this is rigid. And then we made an assumption also on the jump part. This is the most simple possible assumption that one can make. We go from only having one unknown function to having two unknown functions, and one is the jump of the vectorial unknown function, and the other one, h, is the delamination plane. So we're imagining that the body can split and create the delamination function as a surface inside. The main objective is to reduce this. So to obtain a reduced formulation for the energy, and once one made this hypothesis, it's very easy to obtain it, and it comes with a very clean form. This one can see that there is a hierarchic distribution of the terms of the energy. We can immediately identify membranes term, bending term, and mixed So here, in the very dynamic theory of continuum mechanics, once you reduce the energy through the thickness, you obtain a model that still retains information on possible delamination. Okay, so the H function is still an unknown of the problem, it's inside the reduced energy, and the shape of the energy that you get from the reductions shows that there is a coupling between membrane and bending, despite the fact that it's linear. This is something that typically does not happen. So we wanted to, once we have the reduced form of the energy, it is very easy to write out the reduced Lagrangian and then to build a consistent variational approach, and by means of a minimization procedure, it is possible to find the unknown function of the problem for a specific type of loading condition. So we had that model that, I mean, it's analytical and you find a way to solve it. We use the Galerkin approach. And we had some solution. Before I show one of the solution, I want just to say how you can compare. We developed a dimensionally reduced formulation for the very dynamic treatment of nonlocal delamination. And we wanted so to compare it with what the dynamic theory can do. So this is a 3D dynamic discretization of the continuum. And this is how you build it, and by means of an energetic equivalence with standard local elastic model, we find out that actually the energy that two particles in bond-based peridynamic share is that of a truss. So you can imagine the local continuum as a series of nodes, each pair that satisfy the maximum distance condition, connected by a pair of trusses, and you end up with this web of trusses. Okay, so this is how you build the 3D dynamic theory, and then we compare the numerical solution and the semi-analytical solution. We reach the solution independently. This is a list of the parameters that we have implemented in the simulation. You typically choose the non-local parameter defining the non-local model by means of an energetic equivalence with the local elastic one that you want to imitate or reproduce, let's say reproduce. It has to be said at this level that the way that you impose the equivalence in the energy has a slight consequence on the final result of the energy. The coefficient, I will show them later. Some coefficient will differ, will depend on the way that you impose this energetic equivalence. You can impose, for example, isotropic expansion of the dynamic body and then compare it with isotropic expansion of a classical local continuum. So this is the solution for two couples acting at one end. And we can see that the analytical and the numerical model fare pretty much the same. So the theory is valuable from the point of view of comparing it with peridynamic numerical simulation. Why is it useful? Well, when you have a peridynamic body and you discretize and you want to treat delamination, which is happening through the thickness, you want to be more precise, so you increase the discretization. And the number of degree of freedoms just naturally goes up linearly with the number of nodes, obviously. But the number of trusses and of links grows with the square. So this means that the solution becomes slower. You get a slower solution. Okay. No. So once we had this reduced formulation, we've seen that there were the energetic terms were organized with a clear and straight hierarchy, and we've seen that there was coupling between membrane and bending. So we thought, what would happen if we asked ourselves, what would happen if we try to localize the formulation? When I say localization, I mean that we take the dynamic model, which is described by an internal characteristic length, which is the horizon that tells when two particles can interact with one another, and you send that internal length to zero. If you do that, then you pay particular attention to scaling of each terms. You don't want to end up with terms going to infinity or vanishing. So we checked if the displacements were scaling in the appropriate way, and actually found out that the scaling was okay, it was linear, it was natural. It was natural to do this type of localization. No more requirements were to be added on the displacement line. Okay, so this is a localized formulation, and what you obtain at the end is a description of the energy stored in the strain energy stored inside the local plate, and with again a hierarchy of terms, each one with a slight immediate physical interpretation. The one scaling with linearly with the thickness is membrane energy, and the one scaling with the cubic is the membrane energy. And we know that that is so because we have checked it. We know that the dynamic theory can be described as a hyperstatic truss. And we see that actually this term here was membrane and so on. And we can see from the result that there are also even terms, and these even terms usually in the reducer theory they can come out as a result of the reduction plane. So I mean the plane with respect to whom you reduce the model. For example, if you take the normal local plane and you reduce with respect to the lower plane, you might end up having even terms. We have chosen the mid plane, which typically cancel us out these terms here. Even so, we still obtained something that had coupling. So this was a nice result, because in this way we were able to obtain a linearized linear model, which is treating also, which is retaining information also on possible delamination, that had this coupling between membrane and bending. This is something that doesn't naturally happen. We have tested the localized formulation. This is a sensitivity analysis on the bending stiffness, as the delta is the horizon, which is typically a fraction of the total length, as the internal length went to 0. I need to speed up a bit. Okay, so this is, we ask ourselves, just as a final example, what would happen if we imagine the continuous part of the displacement field to be that of Kirchhoff, and then this is the continuous part of the energy that resembles Kirchhoff plate, and this is the addition of the jump part. So this is a reduced formulation for Kirchhoff plate accepting the delamination. As I said before, there are two observations that has to be done here. This one is the curvature. Okay, this is the kinematics that we accepted, but the coefficient is not the same as local elastic theory, and this is due to two things. The first one is that the local theory of peridynamic in bond-based formulation is a one-parameter elastic theory. There is only one parameter that you can you're free to change, because Poisson ratio is fixed depending on the type of situation you have. If you are 3D or strain, plane strain, the Poisson ratio is fixed to 1/4, and if you have plane stress or 2D solution, it's fixed to another value. And the other aspect that is affecting this number over here is the way that you calibrate that single parameter. I said before that the best way is to make an energetic equivalence with a local elastic model, but there are other ways to do that. This was just a choice to obtain something that is resembling what we already know from mechanics. Okay, so I'm going to move now on to the second part. As I said before, I'm going to talk about an hydroxyapatite-based material derived from wood. Why derived from wood? Because natural materials are very optimized, and there is a lot of effort in the literature to reproduce and mimic their microstructure, because they're particularly optimized. And I want to talk about this bioapatite material, which is an organized rosopathy obtained from rattan wood through a series of chemical processes that transform the wood into an oriented rosopathy ceramic. The reason why CNR developed this material is because the material is sought for bone replacement applications, so in biomedicine, and by performing this type of transformation, they were able to avoid sintering process. Sintering processes are high temperature and pressure processes that destroy the biocompatibility of structures. So they were able to produce something that was extremely biocompatible. We've seen it. It is extremely biocompatible, and that is due to the different type of different level of porosity that are shown in the microstructure. So we here at the university we have tested the mechanical behavior, since it's thought for bone, biocompatibility, I mean also induction, conduction, and integration is not the only problem that you have to deal with. You want something that is strong enough to lift the weight of the body. And this is the analysis of the porosity, which is actually what drives the main cause for the second part of this study. And as you can see, the material is a lacunar fracture nature. There are multiple levels of porosity ranging from a couple of micrometers to hundreds of micrometers. These different levels of porosity are actually responsible for the strange behavior that the material has under compression, and this is the result of some compression tests performed. We can see how the bioapatite fare in comparison with standard hydrosopathy. The difference is that hydrosopathy over there is the one obtained from rattan wood, from the chemical transformation. This one is anti-core. This is standard hydrosopathy. It does not have any preferential direction in the organization of the crystals. And then you can see that from the pictures, it's immediate to witness that there is a very brittle behavior exhibited by anti-core, and hydrosopathy has a more slow and progressive failure, which depends on this exfoliating type of failure happening in the contour that slows down the crumbling, for example. And this is the compression test along the direction of the main course. You can see that there is this nice behavior and slow fall instead of normal hydrosopathy, which is not suitable for bone replacement because you don't want something to crumble suddenly. Also, the overall mechanical properties, I mean, strength and stiffness are superior, but this is in the direction of the channels, so this is something that is inherited from the rattan wood. Rattan wood is obviously at least transversely isotropic, and the product and the obtained material is transversely isotropic. So the other direction behaves differently, but it's still better than anti-core. And this is a nice picture obtained from SEM of crack propagating through the sample. We can see that the cracks actually is developing and passing through larger voids, but as we will see in a few minutes, smaller voids have a huge impact. And this is something to summarize the mechanical properties very fast. I just want to say that hydrosopatite is one of the main minerals that made up bones, and its behavior, so it's located along the line that is connecting cancellous bone and cortical bone, because bones are made up of a different percentage of cortical bone and cancellous bone. Cancellous bone is very porous, cortical bone is less porous but stronger, and the material is spun, VA is spun right along the line connecting these two extremal condition, and behaves better than hydrosopatite with still very high percentage of total porosity, which is very good in terms of biocompatibility. I mean, also conduction. So cells need to penetrate the material as much as possible and transform it. So the nice and clean fracture propagating through the sample that we witnessed inspired for our work on that aspect, and we wanted to analyze the effect of this multiple porosity on fraction patterns. We've done it. This is just actually an analysis of standard bioapatite. We have produced, we will use them later. This is just an analysis of the dimension of the porosity, and we have produced a lot of numerical samples that try to recover the geometry of standard hydroxyapatite. Okay, so what is the phase field theory or phase field approach to fraction mechanics and why we have used it? Okay, so the theory is very well suited to treat fracture because it can develop cracks in a natural and spontaneous way. There is no need to explicitly define cracks, for example, when they like they do in cohesive model, or even extended family with a special treatment for the crack tip. This is not required already, so it's very spontaneous. The theory is based on an approximation, which is a topological approximation on the crack shape. So meaning that instead of imagining the body as a 3D element and the surface as being to the surface developing inside, being that itself an unknown of the problem, you imagine the damage to be diffused along the body, and you build up a scalar. You imagine there is a scalar function representing damage defined all over the volume. So cracks now are more diffused rather than sharp. This approximation is useful because it allows the total potential energy to be written in terms of only volume integrals. So usually, from the variational point of view, if one looks at Marigot and Frankfurt approach, the surface where the cracks develops is an unknown of the problem and is an extrema of the integration. But by doing this approximation in the topology of the crack, you actually have volume integrals which are not unknown anymore, the limits of which are not unknown anymore, but you acquire a diffusive field, a scalar field defined all over the body that represents damage. A typical assumption that is done in these cases is this one that is done by Mia in one of his works in 2010. And well, the assumption is very easy to make. You split up the strain energy into a positive one and a negative one. The positive one is associated with traction, with tension, and the negative one is associated with compression, and then you add a degrading function only to the tension part. So in this way, you're sure that the properties are being determined only for tractions and not in compression. You don't have any rupture under compression. So once you have that formulation, it's very straightforward and easy to develop the variational formulation and the finite element. And this is how we did it. We implemented using free software called Phoenix. And we have calibrated the model first. Obviously, we wanted to, sorry about the picture, we lost some definition. This is the calibration of the model. We wanted to first verify if it was able to reproduce spontaneous crack propagation, and actually did. So this is standard benchmark used in phase field. So this is calibration, and we wanted to analyze the effects of single porosity or multiple porosity in crack pattern, and to see if by using the phase field, it's actually possible to reproduce what is happening at the ceramic we're starting to create. So, and this is so the analysis in the case of a single porosity. We have tried out many different levels of single porosity. The overall properties of the models are listed here, and obviously the overall properties they're easily reproducible. There are a lot of analytical formulation to predict the overall behavior. There is the Koppel-King early approach, OH Strickman bounds. They're all very, very good to approximate the overall behavior. But in terms of the phase field, so I mean crack pattern, that is not the case. There is no fast and analytical solution, obviously. There is the MSA method, which is a geometrical one. It relies on a minimal solid area, but it does fair badly also when you try to predict where the crack is going to be developing. So the onset is a problem too. And so the phase field is perfectly capable of developing spontaneous crack. And then we went on then with the multi-scale approach. So here we had a continuum that was not composed anymore by a single scale of pores, so pores with the same maximum radius, but two different scales. And we have compared the result of the simulation with the bioappetite. It was possible to sorry, again. Okay, this is some of the results of the overall properties. We have seen how they change with the total porosity. The model is very is capable of reproducing crack patterns. It's capable of reproducing the overall properties of the material, and this is in terms of overall properties. We have seen that. There is a nonlinear correspondence, obviously, with the scale of porosity in terms of strength and stiffness. And interestingly, if you increase the microporosity over a certain level, you don't get any changes, any significant changes in terms of strength. Meaning that the fact that small pores are inside the model already, it detriments the strength of the material in a reversible way. Okay, and this is the phase field prediction. So this is a small picture, but it's possible to see that small pores are actually able to develop cracks. And this is something that is happening in bioappetite, for example, which has multiple level of porosity, and all the mechanism of fracture are perfectly reproduced by the phase field model. There is nucleation and development from micropores, and there is that also happening from the macro. So macropores and micropores are both responsible for crack developing and crack breaching from one onto the other, and the model is able to reproduce it. This is for two different geometries, but the capacity of the model is well established. Okay, so this is just some of the research outputs and references. The work is still ongoing. We are implementing the phase field for many other things, and there will be papers coming, we hope, soon. And this is some acknowledgements. Thank you everybody. This PhD was an amazing experience, and thank you all for your attention.
Okay, thank you for your exciting presentation. Actually, you wrote two PhD theses instead of one, actually, because there are two different, more related in some way, argument of the thesis. And compliment for your English. Your presentation was really clear.
Thank you.
Okay, I have some question because I'm curious about it. Let's start from the dynamics. I start with the question. If I didn't understand one point. You start with actually a non-linear behavior of the leads of the spring, actually, because they break at a certain point. And then in some way I miss where this fact enter in the subsequent formulation. That's because then you reduce to a linear model. In any case,
yeah, actually,
how does the non-linearity enters into the formulation after?
Okay, so I need to say, I think it's here. Okay, so here, this is a linear constitutive, this is partially linear constitutive relation. But even if you have a linear constitutive equation, model, the behavior is non-linear because it's vectorial, so you have rotation of the position. So when you linearize it, you imagine that there is no significant variation in the angle of application of this behavior.
Finite displacement.
Yes, exactly. So this is very small displacement. That is the linearization I'm talking about, the vectorial linearization. The constitutive behavior was already linear until it breaks, and the breakage, the irreversible breakage, is expressed by, let's see, maybe not here, by this function over here. So it's already inside the constitutive relation. So you don't need to treat it explicitly, because it's inside the linear constitutive. You take this, you place it in the displaced in the equation of motion, and this function over here is an unknown of the problem. So you need to understand if under a certain level of deformation, some bonds are breaking irreversibly. So it's implemented inside the constitutive relation, and it appears. This is the vectorial linearization. This is the relative displacement between 2 points. This is a second-order tensor describing the relative position. It only depends on the displacement, on the relative position. If you don't linearize it, it also depends on the final configuration. This is only depending on the reference configuration. And so this is capturing all the irreversibility and non-linearity
in this term. Okay, yeah. And okay, so in this case, the crack path, the direction of crack propagation is determined by the links breakage.
Yes, it's not immediate.
Then you recover, for instance, classical crack propagation criterion, like, for instance, maximum of stress criterion for the direction of propagation.
Yeah, actually,
does it recover some classical criterion, or for instance, as the delta, the parameter, the nonlocal parameter goes to 0, or even for finite value of delta?
Yes, we have seen that by localizing the model, it's more natural to talk about the localized model. It's more intuitive, and we have done it for many years. So at the beginning, we struggled with the non-local planes. We were talking with Luca, what is a non-local plane? How can I imagine it forming a non-local plane? So this is why we insisted so much in developing its localized equivalent in order to understand it better. And when we localized it, we saw that the energy was being absorbed by the model, even if there is a jump. And this is some kind of cohesive behavior. So you end up with localized formulation which is cohesive in a sense.
So even if you start with a not cohesive, could be a brittle relation.
Actually,
could you take into account for a cohesive behavior since from the beginning, and
yes,
from the constitutive relation of the links?
Yes, of
does
course.
it improves convergence or decay?
It shouldn't have any kind of problem. It has been already done, not in terms of reduced and localization model, but the dynamic does not have ever shown any convergence problem with all kinds of kernels possible, and all kinds of constitutive.
Relation theory in the case.
Actually, they've shown that the dynamic theory through gamma convergence retrieves, converges, I don't want to say converge again, converges to classical local theories. And this is why it surprised us, because we obtained something that is cohesive. Yeah, we know cohesive models, but it has a coupling, and we actually were surprised by the fact that it's not always happening. Coupling between membrane and bending in small displacements. It is something that can only depend on the microstructure. It's obviously a result of the microstructure, which is very complex. And I wanted to say that the non-local model is what is it? It's cohesive by definition, because
not with the breaks.
When you
breaks at the same time, the gradual breakage of the
exactly. They naturally accept jumps. So the real trick here is that this is not necessarily saying that there is a crack. Jumps are happening. They might not break anything. So unless the bonds are break, there is no crack.
With this formulation, you can recover also passing the crack, not only in the thickness,
Yes,
but
you can get
every kind of cracks.
as long as crack is defined by a function. It has to be defined by a function. So you can have like something even going up as much as possible, or having jumps in the only condition is that it has to be a function, and it has to be. It doesn't need to be derivable. It has to be it doesn't need to be continuous anyway, because the derivation of the displacement will happen. That is the real strength of the model.
Just a final curiosity, then I leave the question to my colleague. In the energy reduction, the integration has been performed analytically.
Yes, in closed form.
Okay. Up to you.
Okay, so first of all, also on my side, congratulations for.
Thank you very much.
As Enrico mentioned, it is apparent that we have been attacking two different problems of fracture by using two different formulations or approaches, right?
Yeah.
So as a first general question, since we have been working on this for years, I would like you to comment about the pros and the cons of the two approaches. So somehow, when one develops, to interpret my question, somehow when one develops a approach to fracture, maybe, the final goal is that this approach is maybe suitable for a large set of problems. Right?
Yeah.
But maybe there are restrictions about the applicability of one approach,
Okay.
right?
Okay. So.
Or in other words, any chance of extending dynamics to the study of fracture, physics, and porous solids, or the other way around, extending the phase field approaches to delamination problems?
Okay. As long as phase field is concerned, phase field theory has been used to deal with delamination because it naturally treats cracks. It allows them to develop in a very natural way. The only problem with the phase field theory, we see that you struggle a lot with the quantitative measuring of your tests. So qualitatively, cracks behave in a way I didn't show them, but we've compared it with a lot of experiments, and successive papers will deal with that. And it's very easy and natural to reproduce qualitatively these results. The real struggle is from the quantitative point of view in terms of force displacement. So each case needs a special treatment. So I would say yes, it's possible to treat anything, but it actually very much depends on the type of loading, because the model is very sensitive to minimal differences, because as you've seen, the damage function in the strain energy is a continuous function, and so the degradation is progressive, and the minimal mistake can lead to crack propagation beginning and developing where you don't want them. So it's very hard to
the model.
you need each and every case need to be treated separately. But the theory in principle is very clean. It's very it's very clean. Whereas the dynamic theory of continuum mechanics doesn't have a lot of analytical solution to begin with. It's a numerical model, and its strength is in the high discretization and parallelization of software that are using dynamics. So by brute force, you discretize all the continuum, and this is similarly done because dynamics is the natural extension to continuum mechanics of molecular dynamics. So it works pretty much the same. You have potential defining the behavior of two couple of points. The only difference is that in molecular dynamics you cannot have chemical potential to. But I don't want to talk about that. And so from the numerical point of view, the dynamic theory has been used to treat a lot of problems, impact problem and fracture problem. It's very natural to treat it. Analytical solutions are not so spread in the literature, and this is I believe one of the few cases in which you can make simple assumption and obtain something that can, at least in principle, be treated analytically. By treating analytically this, you can have a better insight of what is happening, because you, as I said before, we struggle a lot with the physical interpretation of the non-local plate, because we were not used to local models. It's not immediate. We are engineers. We work with concrete and steel, and we have been taught the standard local theories to be perfect. And I would say that the strong point of plate dynamics is the fact that it's possible to treat fracture problems in a natural way, but it's at the same time very hard to treat it not numerically. And so there are certain conditions, again, where this model can be applied. It depends for this model, depends on the fact that these are functions. And if you want to deal with multiple delamination, you need to add multiple jumps field over there. This is in a sense very specific, but it can give us a result that is generic in a way, because for delamination, for a single delamination, the result is physically easy to interpret. So there are a lot of restrictions. I would say that for the phase field case, also analytical solutions are very, very complicated. And if you have, you typically treat, we've been treating poles, and we were not able to obtain any analytical solution for the strange patterns followed by the cracks at each loading step. They are very strong, but they have weakness that depends on the fact that you need typically to have a numerical model to obtain the solution of a specific problem. This is just one of the few cases in which you can obtain something analytical by performing a rather significant approximation. I mean, in a sense, it's an extraction of the type of failure involved. I hope I answered the question.
It was kind of general question. And as a second question, would you be so kind to guide me along the main steps to get the reduced energy? So is there an answer about the U alpha field?
Yes, this is the continuous part, and the answer is just the hypothesis of thin element. So you take the continuous part and you Taylor expand, but this can just be a function expansion. It doesn't need to be a Taylor expansion through the thickness. And this is legit all the reduced formulation deal, because when you want to reduce something, you need to integrate another formulation. You need to integrate, and if the integration variable is not explicit, it becomes impossible, almost impossible. So this is the way that we treated the continuous part, and the jump part. We wanted to keep it the more general possible, and so the jump is composed of a jump function. This is giving how much the point will jump in the new configuration, and a delamination function, which is put inside a heaviside function that is localizing the. This is to localize when I say localize, it's to pinpoint all the part of the bodies that will go through jump. So there is something that is not jumping and something that is jumping, and is identified by this function over here, which depends on the delamination function. Then when you do these two answers already, this is the most general way possible. I mean, we started from one field, vectorial unknown field, and we have only two here on this side. So we pass from 1 to 2, and in this way, since the thickness variable is explicit, you can grab them, put them here. This is the relative displacement. So you take the displacement that you have, and you integrate.
And then you extract all the terms at different orders.
Yeah, actually here I just realized there's a mistake. This is
Yeah.
something that I copied from a previous version. The integration is from minus h square h divided by 2 to minus, because the reduction plane is in the middle. It's not there. There's a mistake.
It's still unclear. The UJ, I mean, about the UJ that you assume.
Yeah.
Is it somehow prescribing the crack path or the crack topology that may arise during the simulation?
Yeah, it's
So there is a prescription.
yes.
Okay.
It's gonna be a
Because your sketch, you know, I'm seeing something which may curve or
yeah. It can. It
it
can.
can.
It can. It is expressed by this function over here.
I mean, about the dynamics of the last question, the numerical implementation, right?
Okay.
You were mentioning the nets, right?
Yes.
So there are dots, nodes, and
Yeah.
then
Dots are nodes.
crossed elements.
Yes. The dots are nodes, and then if you take the dynamic formulation and you integrate the energy over very small volumes, so to see, because these couple of points have a force that are exerting one onto the other, which is dimensionally a force per unit volume squared. So you need two small volumes, and you integrate it, so you average the energy, and you obtain how much amounts the energy of a couple of particles. And this is the result. And then you compare it with standard local energy, and you see that actually this energy resembles that of a spring truss, so that it can only withstand compression. And so it is possible to imagine the non-local continuum as just a local model. The numerical model is a local one, where you have nodes connected with standard local beams. But these beams are connecting faraway nodes in an hyperstatic way, and that is where you retrieve the non-local behavior. And this is how you build up the...
Yeah, but my question more specifically is about the following point. So, I don't know, suppose we call small k the stiffness of phase
Okay.
3. And we call E, capital E, the Young modulus of the, say, effective solid.
Okay.
Is there a dependence
Yes.
of E on the geometry
Yes.
of the net? How do you-
Yes, of course.
I mean,
The
this
best
question
way-
comes from the fact that typically when you study periodic structures,
Mhm.
some of them are isotropic, some of them are not isotropic, and the effective properties depend on the topology.
Of course.
And so I
Yeah.
wanted to understand whether the net that you choose to discretize and
Well-
I mean to implement dynamics numerically
Mhm.
affects the
It does. You need to, because these trusses need to have stiffness, you call them K, and in order to write out this number, this K, you have to perform, you have to calibrate this parameter, and typically it is done by means of a volume integral of the non-local energy. So you want that the specific volume energy of the peridynamic model resembles that of your local material that you want to reproduce. And by doing that, you actually have to integrate over the volume. So the shape and the connections directly affect that value. So all the microstructure and the extension of this grid depends a lot on the maximum distance at which two particles can interact, which is called the horizon. And the shape of the horizon directly enters the integration. Because when in peridynamic you have a double integration, so you have a first integration, you can imagine it as you're fixing a particle and then you're integrating while moving the other particle between all the other points. Obviously, when you're outside the horizon region, when you're inside the horizon region, that is called the family. They've used this name in the peridynamic. It's called the family of that specific point. When you are in the family, actually you get something. When you're outside the family, you get nothing. So the integration for the other, so the first integral that you perform is actually not in the whole volume, but in the shape of the family. So it is there that the shape of the structure of the non-localization in the structure affects the overall behavior. It is just in that sense. But this is obviously for the case of bond-based peridynamic. Bond-based peridynamic is just one of the possible models. There are more advanced formulation that avoid the fact that this is a centered trusses, so the Poisson ratio is fixed. You can free Poisson ratio by upgrading to the bond-based formulation. Basically, what is happening is that you imagine a couple of points with a more complex energy to be not representable anymore by trusses, but they have an interaction which is not defined by a single parameter, but rather a matrix, giving you the stiffness, the relative stiffness for all the relative displacement. So yeah, it's affecting the integration directly, the shape of the horizon and the shape of the family, and the resulting energy and the stiffness of the beams are directly affected through this equality.
And the very last question about the phase field approach.
Okay.
You mentioned that you had to start by calibrating the model, right?
Yes.
Because yeah, it is clear why you need to calibrate the model, but could you comment what are the parameters that you had to calibrate and how you actually calibrated them by looking at, by comparing, I guess, experiments and the outcome of simulations?
Okay.
What is the set of parameters?
The set of parameters is just the fracture energy. This is the fracture energy intended in a Griffith sense. And so you need to calibrate this. This is the first one. The second one is represented by it's this L over here. It's the regularization parameter, and basically it's giving you because when you do the topological approximation, I said that the crack is no more a crack, but it's a diffusive damage. The more this regularization parameter is sent to zero, the more the damage volume converges to a line damage. So the regularization parameter is giving you the accuracy of the model with respect to the classical solution. This is the second parameter, so L and G of C. And then the model is elastic, so it needs this is isotropic elasticity. So you need the parameter of the
parameters.
And so I would say 4 at this level. 2 from the linear elastic and 2 from the fracture.
That is the K in GS, right?
This one, this is just to avoid zero stiffness and rounding errors in the simulation. So actually in the analytical treatment we have avoided reporting them. This one, but this is explicitly inserted into the damage function. So you have these 4 parameters. Obviously, the elastic part is very easy to calibrate it, and whereas
so you get before fracture, actually, of course, you already
you
determine lambda and u and domain parameters. That's it. And then you are left with L
and G of G small c. The fracture and the regularization parameter. Now, these 2 parameters affect maximum strength of your model, so which is the maximum tension that the model will show, and it affects also the total absorbed energy. If I show you, it's the area beneath these curves over here. It's G of C and L. They both are calibrated in this sense. So you have your curve, and then you just You can actually estimate these values by using very simple one-dimensional, usually to this. You take a very simple one-dimensional phase field formulation, and then from this analytical solution for the 1D case, you know that you can expect the strength to increase when you decrease the regularization parameter. You know that the same is happening for G of C, and then you begin from that and you start brute force changing. You try to perform several simulations until the energy absorbed by the total model and the stiffness, strength, the maximum strength reaches the level that you want to reproduce.
You did it manually or by means of optimization procedure?
No, we did it manually. It's the fastest way. The simulation can be very, very slow, especially for this kind of problems. And okay, yeah, that's it.
Thanks.
Okay. So, congratulations for your work. So, with regard to the second part, please go to the slide where you mentioned the splitting of the energy. Okay, so here. So during the presentation you mentioned that you have a positive energy and negative energy.
Yeah. The positive part and the negative. You split up the strain energy in this way.
Okay.
Like this is the strain tensor, linear, small displacement strain tensor, and then you split up in this way. And the formulation, this was implemented first by Minier. It's thermodynamically consistent. Still retain consistency from the thermodynamical point of view. So it's legit.
So, but sorry, I don't understand. What does it mean, epsilon plus or minus?
This is the macro bracket. So you take the trace of the strain tensor, and then when for the positive part, it becomes 0 whenever this is negative, and it's still retains the same.
How you decompose epsilon in a plus and minus?
You do the eigenvalues split.
Okay, so you take the initial epsilon, then you divide it,
Yeah.
decompose it. Okay, so
I didn't put them here. I think we can. I forgot to add them over here too. Sorry, it's in the paper that we.
Okay. So eventually you have really a positive strain energy and a negative one.
Compressive, yeah.
So what do you mean?
There is
then the strain energy is positive for both parts or not?
the strain energy is a positive quantity. It's just associated with the compression
So it was
part.
a bit misleading that you defined it.
Oh, sorry.
Part.
No
problem.
The symbolism is not our.
No, it's okay. But since you say positive and negative part,
Yeah, sorry.
but still
I understand
positive.
now.
Okay.
Sorry.
So, as far as regards the first part, can you go please to the very first slide?
The first
Yes.
line.
It was maybe the third or the fourth, where you define the bonding behavior. Okay, here. So, I understand that you derive a model that is non-local.
Yeah.
Okay, so you eventually consider a solid, and then you discretize with points, and these points are connected to each other.
Yes.
Okay. So, first question, if you, let's say, refine the mesh, what happens to these parameters, mu, S0? I mean, if you want to have, let's say, a model converging to the same behavior.
Mu is just a function that is defining when the. Okay, so this is the behavior that you want to reproduce. You just need two informations, and these informations are just the slope of this line, and then the threshold for breakage. And these two parameters, they go inside of F, but we have treated it analytically. So from our point of view, there is an infinite number of points through the thickness. This is still, this is at the, we have discretized the body, but I don't mean that there is, for us, a real distance between these particles. we mean that through the thickness at least, because the reduced formulation was obtained by performing only through thickness integration. You can then perform the other dimension integration, but we didn't that at the level. And through the thickness, the number of there is no explicit discretization. What I mean is, obviously, there are some studies that, from the numerical point of view, because this is all analytical. This is just.
Sorry, because then later when you reported the slide with the title localization,
Yeah.
you shown, for example, points connected. Okay, here. I mean,
Okay. No,
you have now. I mean, that is the thickness of the plate.
Yeah.
Okay.
Yeah.
So my question is, maybe you can also refine more
Yes.
to the thickness. What happens? What
You-
should you do to the initial values? For example, S0.
No, you can leave that. You don't need to. I mean, those two parameters need to be calibrated each time that you define a refinement. In particular, if you want to reproduce a specific behavior, which is that, for example, of glass, that it has a fixed Young modulus and it breaks consuming a certain defined amount of energy, what you do is you use energetic equivalence between your numerical discretized model and analytical local solution. And there are actually two very easy formulations that you can use to calibrate these two parameters in order to have the same overall stiffness, which is what you want, and the same overall consumed energy for fracture development. Okay, so when you increase the discretization, you are increasing the number of bonds. So crack propagation in peridynamics means that you have to cut more bonds. The more bonds are cut, the more energy is stored. So the more energy is stored, but since you want to keep the overall energy consumed by crack propagation to be the same, you need to reduce the critical elongation so that each bond can store a less amount of energy. This is just a direct consequence of the fact that numerical simulation explicitly require a discretization through the thickness, and the calibration in that case is specific for that case. Whereas in our model, it is still kept analytical. So you obtain the reduced formulation, and you at that level can still decide how much is the critical elongation in order to reproduce the fracture energy that you want. So once you have the reduced formulation, that is the time that you can act on the parameters to correctly reproduce an everyday phenomenon.
Okay, because the second part of the question is, I mean, both from this type of implementation and also on the analytical side, I would expect that you should have a sort of convergence reached when you decrease enough the distance between the points.
It depends
or
on
you decrease, I don't know, the S0 or... no?
Yes, there are several types of convergence in peridynamic. First of all, you need to talk about convergence to what? I have a local model and I want to converge to the result that the local one is giving me, and increasing the mesh does not affect that. But on the other side, you have another type of convergence, which is I have a local material that I want to reproduce. The local material is built up by an infinite number of particles, but I am discretizing it, assuming there are just 2 or 3 in the thickness. This is an hypothesis that I am making. By increasing the number of points, so by increasing the discretization, I'm converging to the real non-local solution. So you need to differentiate between what type of convergence you want to obtain. You can converge to non-local, like we usually do with numerical models, or you want to converge to a local one.
So do you have also a convergence in terms of the spring connecting not the closest nodes, but also the
Yes. Yes. Well, in
sorry,
what
and
sense?
the spring, how is tuned? You are taking the same stiffness or the first one?
No, it depends on the on the uh, on the overall energy that you want to reproduce. If you want a specific energy per area, per volume, defined in a certain sense, then you want that the integral over the family of points connected to that specific point need to be a certain amount. So at that level, you just have, for example, here, one value of the stiffness that you want to obtain, and here you're already making an assumption, which is that every bonds have a different stiffness. Okay, the same stiffness. Since these are trusses, it means that the more the length of the truss, the smaller the area, and then if you want, I know what you ask me. What would happen if I would change the stiffness the more the bonds were far apart? Then you would reproduce a different level, a different model of the dynamic kernel. Okay, so this is a kernel in which the stiffness that 2 points are exerting onto one another is constant when the bonds are more far apart. But then there are also other models in which the stiffness can grow as the particles are more far apart, and in these cases you end up having a numerical discretization that has bonds that are far apart, which also have higher area, and so the stiffness is not reduced but is increased. So it's a reflection, the way that the stiffness goes by increasing the distance between 2 points is just an assumption that you made at a local level on the kernel of the local integral. And all of these models, all of this, they don't have any convergence issues for the local model. So if you take one of these kernels and you implement it in your local model, and then you want to localize it, you never end up having troubles with this one. They're just a family of one parameter function.
Okay, I have some question about the second part. And can you tell us how practically ceramic is made from wood? How
Yes.
it is practically realized, actually?
This is very interesting. Typically, you have your starting material, and then you perform a series of chemical transformation, which relies on sintering, and you obtain the hydroxyapatite. But the novelty of this approach is that they took the parent material, and they, instead of injecting the hydroxyapatite, which is just a combination of calcium and I don't know how to say those names in English of the other components. But the novelty is that you take the wood and first you burn it, so you obtain carbon, and then you build the hydroxyapatite on top of the carbon structure. So you have a carbon template, you have a carbon template, and you attach to this template the other components that made up hydroxyapatite. Typically, this is not the way it was done, because what you typically do is that you have a structure and then you inflate the constituent of the hydroxyapatite, and they deposit on top of the structure, which is then burned through sintering processes and completely cancelled. And what is left is this something made of hydroxyapatite, but it is built on top of something that there is no more. There is no more. So the result that you obtain in stiffness and strength of the hydrocephalite, the behavior is actually performing better than normal hydrocephalite, and that is due to the fact that by transforming it, you make so that the bonds between the molecules is stronger.
So the increase in toughness that you observed is mainly due to the wood structure or to the porosity, like for sinter or incompleted sinter or porous ceramics. So it's responsible of increase of toughness,
Yes,
the wood structure as well.
It is mainly responsible. It is mainly responsible because, as you can see from the Ashby maps, the average porosity between standard hydrocephalite and this composite, this ceramic, is almost the same. The range is almost the same. You see, there are some with a lower porosity, but some others will have higher porosity. So on average, it's almost the same. But with that level of porosity, you are obtaining something that is optimized. So you organize it in an optimal way, and that is immediate in the result. And as you can see, this is very nice because the bioapatite is bridging between the parent material and the constituent. Because the constituent of bioapatite is that of hydrocephalite, but the structure is that of wood, and that is bridging in between the two.
Okay, thank you very much for your answer, your clarification, and now you can get rest and we can pass to the next candidate.
Good morning, my name is Rossi, and the title of my presentation is Dynamic and Stability of Discrete and Continuous Structure, Flutter Instability in Piecewise Smooth Mechanical Systems, and Cloaking for Wave Propagation in Kirchhoff Plates. So let's start with a brief introduction. This presentation will be divided into two main parts. The first part deals with the cloaking of flexural waves, so deals with continuous structure. And so the problem of cloaking of flexural waves in thin elastic Kirchhoff lock plates. The second part deals with discrete structures, and in particular the stability and the equilibrium in piecewise smooth dynamical system, and in particular paradoxical, let's say, behavior of this kind of structure. So let's start with the first part, so metamaterials for the cloaking of flexural waves. What is a metamaterial? Metamaterial is a particular kind of material whose behaviors depend on the internal microstructure. So the aim of this first part of the presentation is to try to design a microstructure in order to create a sort of invisibility cloak for a hole in a thin elastic plate with respect to the propagation of flexural waves. So the main theory was developed by Colbit in this paper. And the starting point is the equation that describes the equation of motion of a homogeneous elastic plate, isotropic plate. So the classical sufficient Lagrange here. You can transform this equation into this that describes the vibration of this plate, and it's a fourth order partial differential equation. What happens when we perform a transformation of coordinates? For example, we can pass from a plate with a small hole to a plate with a big hole. We can use a coordinate transformation called F, and also the equation of motion changes, and this is the final result. So a complete fourth order partial differential equation. You can see all the terms, and this depends on the parameters of the transformation, of course. So it depends on G, J, and F. So this is the idea. This complete fourth order partial differential equation can be associated to has the same structure actually of the PDE that governs the behavior of an inhomogeneous anisotropic plate with in-plane plus stress. So they are the same equations if we perform this identification of the parameters. So this is the main idea. So let's imagine to have an homogeneous isotropic plate with a small hole. Then we can transform it and we obtain a transformed homogeneous isotropic plate with a big hole. And nothing changed in the physical behavior because the behavior is the same, only the mathematical perspective changed. Then we can associate this one to an inhomogeneous anisotropic plate with a big hole. And also here, nothing changed from a physical point of view because we have the same equation. So this behaves exactly as this. And so if for an homogeneous isotropic plate with a small hole, the hole is too small to disturb the wave propagation, also for this plate, the hole does not disturb the wave propagation. So this is the main point of this theory. This is the geometry that we analyzed. So a small square hole and a square cloak made of 4 trapezoids that are transformed using this equation. So this is the idea. The problem of this theory is that we introduce something which is not feasible from a physical point of view. So the membrane force and the in-plane plus stress are very difficult to implement in a physical example of a cloak. So we decided to introduce a computational model and try to find an approximation of this cloak in order to design a proper one. So I started from the strong formulation. I obtained the weak formulation using the relative method. I obtained the discretized form, and this is the final set of algebraic equations that must be solved. I have written a finite element code using MATLAB. It's a general code, and you can perform a lot of things. Maybe you can perform static analysis, modal analysis, time harmonic, and the transient analysis that I will show you in a minute. And using this finite element code, we started to analyze an approximation of this invisibility cloak. This is the geometry of the problem that we analyze. It's a square plate, homogeneous and simply supported. It's made of steel, for example. The thickness is 1 millimeter. And on the center of the plate there is a point force and a harmonic point load. And here there is the cloak, the hole that we want to shield from wave propagation. These are the results. So you can see on the left the disturbance due to the presence of the hole, and in this case the cloaked solution. So you can see that a disturbance is still present, but the wave here is reconstructed in the correct way. There are problems with amplitude, but this is an approximation of the cloak. We introduced also an error measure in order to understand the quality of this cloak, and as you can see, the perfect solution would be E equal to 0, so we have an increase in the performance using this cloak, this approximated cloak. Then we extended the analysis to the presence of a vinculaire soil under the plate, and so we understand that using this mathematical numerical approach that it is necessary also to transform the subgrade modulus of vinculaire. As you can see here we have a cloak, but the subgrade modulus of vinculaire is constant, and the solution is not good. If we transform the subgrade modulus in this way, you can obtain a better solution, and you can see it's better also from the quality measure here. Then there are also some section cuts that show you that the dotted line, which is the plate without a hole, and the red line, so the cloaked solution is they are closed, so the solution is good. And so if we want to design a cloak, we have to focus on the stiffness of the cloak. They are inhomogeneous stiffness, so they change in space. And it's possible to define a local reference, principal reference of orthotropy, and the stiffness matrix assumes this form. In particular, from this theory, this term, the torsional terms, must be equal to 0. And this is a particular feature of this cloak. And so, in order to, this is not easy to obtain in a physical sample. So we performed a sort of sensitivity analysis in order to understand the importance of this term. And as you can see here, we can see the detrimental effect of dx yxy, which is different from 0. But you can choose the level that you want, and so you can obtain a good approximation. So this is the proposal of our plate. So it's a metal plate, let's say, is composed of boron fibers embedded in a epoxy matrix. And so there is a core, so plate here, the one depicted in yellow here. And this is the part that gives this torsional term. So this must be reduced. Should be very thin. The height here should be very thin. And then, in order to obtain the other great stiffness component, we had to add to this plate, to this core, a set of teeth in order to increase the stiffness along this direction. We discovered, so it's possible to tune all the parameters of the plate, the geometrical parameters, in order to fix those two components and reduce as much as possible this one. Then at the end we discovered that also this term is important. As you can see here, also here you can see the detrimental effect of having a dxxyy, so the term which is outside the diagonal, which is not the one predicted by theory. So this must be investigated maybe in future works in order to understand better how to design a proper invisibility code. Then we can start to talk about the second part of the presentation, so flutter instability in piecewise smooth dynamical systems. And the aim of this part is trying to create a sort of link between flutter instability and discontinuous mechanical systems. So this is the aim. What is a discontinuous mechanical system? They are called by mathematicians piecewise smooth mechanical system. They are described by this kind of equation of motion. So a set of ODEs that depends. So there is in the phase space there are more than one subspace, and in each subspace there is a different equation of motion. So there is a switching condition that states in which of the equations of motion you have to consider to solve the problem. Also, if you linearize this problem, you obtain this so-called piecewise linear dynamical system, which is still non-linear due to this switching condition. They are also called Philippov system due to the Russian mathematician that studied this. And they are very common in nature, so you can apply this piecewise smooth model to model dry friction, unilateral constraint, impact problems. So from simple one-dimensional examples to more simple systems to real mechanical systems. And in particular, they are very complex to analyze because from a theoretical point of view, they are not so simple. Philippov developed a framework for the theory, but it's not so easy, in particular because you cannot use classical theorem, so the Apple's theorem or Lagrange-Dirichlet theorem. So they are a bit complex, and when I was studying them, I found this paper written by some Spanish mathematicians. So the matching of two stable systems can be unstable. So I started to wonder if it's possible that this to obtain this counterintuitive and paradoxical behavior also in a mechanical structure. So I started to analyze two simple, smooth, classical models, two stable model. I combine them, and this is the result. So, instability. And so the answer is yes, it's possible that the matching of two stable mechanical systems is unstable. Now I show you how to reach these results. So the physical model that is a reference, that I took as a reference, is this. So a rigid bar, which is loaded with a follower force here, so a force which is also always parallel to the bar. And on the other end of the bar, there is a hinge, and this end is constrained to move on this smooth profile. Then there are also two springs, so torsional springs and a rotational spring and a longitudinal spring. And it's a 2-degree of freedom system, so we need two Lagrangian coordinates to describe this system, so in particular this angle phi and this arc length c. And it's a smooth system, so we can study the kinematic of the system, we can model the force, and then using the principle of virtual mode, we can calculate, obtain the equation of motion, so the nonlinear equations of motions. We can also linearize them in order to simplify a bit the problem. So we can linearize them near the configuration that you can see depicted in gray here, so this straight configuration, which is assumed as an equilibrium configuration, and then you obtain the classical structure of a linearized system with mass metrics and stiffness metrics. And you can try to parameterize the green curve there using different curves. So you can study a curve with a circular profile with a positive curvature and with a negative curvature, or both in this combination of the two. And it's possible, so trying to define the parameterization, calculate the mass and stiffness matrix, performing eventually a non-dimensional analysis, and obtaining this final equation of motion of the piecewise linear non-smooth mechanical system. Here you can see the dependency of one of the two Lagrangian parameters, and so if c is less than 0, we have this equation, otherwise we have this one. We have to study the stability of the system, so we can start with the stability of each single part using a Lagrangian formulation, classical for engineers, or an Hamiltonian description that I used in this work. So I use this formulation. This is the solution in terms of the matrix exponential of the mechanical system, the linear system. And this is the eigenvalue problem that must be solved in order to understand the stability of the system. The stability depends on the nature of the eigenvalue of the Jacobian matrix. And so the eigenvalue depends on the invariant of the Jacobian matrix. So on the basis of the nature of the eigenvalues and of the invariance, you can have here a stable system, here a stable system revealing flutter instability, or here a system revealing divergence instability. So here you can find the information about each single subsystem, but there are not. We need something more to understand the stability of the entire system, the entire compound system, and so we need something more, and it comes from mathematics. So the unstable matching of two stable systems is associated to the presence of an invariant cone in the phase space. This is the key point. So since you don't have any information about any criteria to understand the stability, you need to look at the solution, see if it's possible to find a particular family of solution, and then if you find this kind of solution, maybe you can say something about the stability of the system. So we need some mathematical tool maybe to understand better. So what is an invariant set? An invariant set is a set in the phase space, which, if you, roughly speaking, if you start on this set, you will remain on this set forever, and it's attractive if starting with initial condition near the set, you will tend to the set for t that goes to infinity. Another important tool, mathematical tool, is the concept of Poincare map. So in the phase space, you can define a plane which is called Poincare section, and you can describe the dynamics of this system through the map of the point of this plane onto the plane itself, so following the evolution of the system. So maybe the point y here goes to the point p of y, so the mapped point, along this orbit, so along the orange orbit. This is the concept of Poincare map, and it's important to pass from a continuous time dynamical system to a discrete time dynamical description of the dynamical system. And this is how it's worked the solution. So we have a yellow plane which is called switching manifold, which depends on this switching condition here. Then you can start from the switching manifold. You start from this point, for example, you enter in one of the two subsystems. The evolution follows the blue orbit here, for example. Then you hit the switching manifold, and then you pass in the other system. So in the red one, you start a new evolution of the system along this orbit, this red orbit, and so on and so forth. And this is one approach, the continuous time approach, and then there is the approach using a Poincare section that creates a sort of map between only the point plane on the plane. So this is the concept of discrete dynamical systems. So the idea now is try to find this invariant cone. And so to find this invariant cone, I used two Poincare half maps. So we have to start from point x here, and then follow the blue orbit here until we reach the point c in a time t minus. And then from c we can pass to eta, the point eta, along the red curve, in a point t plus. T minus and t plus are two time intervals that are function of the initial condition. So t minus depends on x and t plus depends on c. And if the point x and the point eta are on the same straight line, passing through the origin, which is the equilibrium configuration, we have an invariant cone. This is the definition of invariant cone, which can be written in this way. And this is a sort of eigenvalue problem, a non-linear eigenvector problem, actually, because the matrix here depends on the eigenvector. And so it's complex to solve from an analytical point of view, but if we are able to solve it, we can use the information on the eigenvalue and the multiplier to state something about the stability of the origin, which is the equilibrium configuration. We have these three cases. So with mu greater than 1, in this case we have an orbit that spirals out, laying on the cone and spiraling out. So it's going far from the origin, which is the equilibrium. So this is a family of solution, of unstable solution. They are going far from the equilibrium configuration. If mu is equal to 1, we have a set of periodic solution, and if mu is lower than 1, we have a solution that is spiraling in. So due to the asymmetric definition of stability of Lyapunov, we can state that in this case we have a non-stable system because we have found a solution that is unstable. In the two cases, we cannot state that the system is stable. We only found out two stable solutions. We should analyze all the possible solutions to state that these two systems are stable. This is not enough for engineers because we need also attractivity, but we will see at the end of the presentation. So now I described the mathematical part, and here, what about the physics? Because this is the important part. How a mechanical system could behave, could have this behavior, and the answer is in the mechanical energy. So if you study the mechanical energy, which is this, you can see that if you have two stable systems and two conservative systems, if the systems are conservative, you have a constant mechanical energy, and so this phenomenon is forbidden. On the contrary, when you have a non-conservative force, the mechanical energy is bounded because the system is stable, but it oscillates in time. So we can have oscillation of the mechanical energy, but the energy remains bounded. Since we have the switching of the system, we can sum up only the increasing part of this oscillating energy. And so we can obtain an energy that increase. So here you can see that, for example, you can start here. You see you follow this bounded solution, so this energy. You can see that it's bounded, but here you have a switch, so you have to pass to the other system, and so you have to start this evolution, which is bounded, but here you change, and so on and so forth. And so it's possible to demonstrate that when there is an invariant cone that I have described before, you have an exponentially growth of the energy, and this is flutter. This is called flutter in smooth systems. So there is a sort of flutter-like instability which comes from stable subsystems. So this is the physical reason. Now we need an instrument, a tool to be able to compute the presence of cone in the system. So I developed a numerical algorithm in order to understand if a cone is present or not in a mechanical system. Actually, we have two main approaches from engineering language. So there is the check approach. So all the parameters are fixed. I give you the initial condition, and the only thing is to integrate the equation of motion in order to find the solution. There is another approach, and in this approach you have to follow the solution, because you have to switch each time the solution, so the equation of motion. There is another approach which is I call the design approach, in which some parameters are known and some other are free. And so you have to state a priori if a cone exists, and it's possible also to find the initial condition of the cone. So this is the description of this second approach. It's a bit hard now, and a bit late maybe, but so you can, I assume that the only unknowns are t minus and t plus, the two time intervals. You can rearrange all the definition of the cone and other equation, and at the end you arrive at this final equation. So there are two equations in two unknowns, non-linear equation actually. And so you can solve, obtain the values of t minus and t plus, and then everything is known as for the cone. There are some problems, because in this approach we didn't follow the solution, but we state a priori if a cone is present or not. So we introduced it in the algorithm. Let's say we introduce it. It's possible to introduce some spurious solution that must be neglected. And so this is a way to avoid this problem, and the idea is try to find a domain for t minus and t plus, in which I'm sure that I can find all the first intersection of the orbits. Say, in the definition of the cone, you must have the first intersection, the time defined as the time of the first intersection between the orbit and the switching manifold. If I can find all the intersection with this algorithm, and so I have to discuss some solutions that are not feasible in this case. It's a bit hard, but I was able to find a bound, so I'm able to find a domain in which I can see all the first intersection, and I can say, yes, here there is a cone, or no, in this system I cannot find an environment. There is another check here, because we must check if we are entering in the correct domain and leaving the correct one. So is a simple check at the end. In this kind of system we have only crossing conditions, so we cannot have a sliding along the switching manifold. This condition must be checked, and so at the end we have the cone. Attractivity is important, because for a mathematician, only one solution, one unstable solution is enough to say that a system is unstable. Not for an engineer, because we can go to the lab, and to see in the lab the instability, we need a neighbor of the initial condition in which you can find this behavior, this unstable behavior. So the cone should be also attractivity for us. So it's possible to study that activity in classical ways for classical smooth systems. So with Taylor expansion, you obtain this formulation. So a fundamental solution matrix which links the initial perturbation of a fundamental solution, so D1 naught, and which links the initial perturbation to the perturbation at a time, general time t. So for a periodic solution, when you have a periodic solution, it's interesting to understand the evolution of the initial perturbation after one period. And so this fundamental solution matrix is called monodromy matrix. And due to the fact that this is the composition of the monodromy matrix, in order to see what happens after each kt, after each k period, you can study the eigenvalues of this monodromy matrix, and from the eigenvalues, which are called cloaking multiplier, you can obtain information on the attractivity of the system. When you consider a piecewise smooth system, and in particular with an invariant cone, you don't have a periodic solution, but it's very similar to a periodic solution. So it's possible to introduce also here a monodromy matrix, and so it's possible to study the eigenvalues of the monodromy, of this monodromy matrix, in order to understand the attractivity of this invariant set, of this invariant cone. We must be careful, because to analyze the monodromy matrix, we have to introduce these two metrics, which are called saltation metrics, that correct the perturbation, because sometimes the fundamental solution and the perturbed one can be in a different system, so subsystem. So maybe one is in the red one, and the one in the blue, and so we have to introduce this simple metrics in order to correct these factors. And so I was able to demonstrate these 8 properties that I think they are very beautiful, because they deals with general mechanical system. Every 2-degree mechanical system fulfills these conditions, and these are the final condition dealing both the existence of the code and the attractivity of the code, because we deal with the point-graph map and the monodromy matrix. And so it's possible to state for any general 2 degrees of freedom mechanical system, piecewise mechanical system, that when mu is different from 1, when we found a cone with a mu different from 1, we have always an attractive cone and an unstable configuration. Otherwise, if mu is equal to 1, we have a periodic equilibrium configuration, and the cone is not attractive. So we are interested in this kind of cone. Then, some numerical solutions. So this is the case that I've shown before. This system is stable, as you can see from the plots. This system is stable, but this system is not stable. You can see that in the GIF, you can see that we started to oscillate and to have flutter instability, as you can see from this picture that describes the evolution of the Lagrangian parameters in time. And here you can see the projection of this cone onto the phase portraits. And so you can see the projection of the cone, actually. If it's possible, from a physical point of view, it's interesting to note that this flutter-like behavior can be possible both for compressive or tensile fall-over force. So here you can find an example of an invariant cone for a compressive fall-over force. They are topologically the same. The solution is different, but because there is an evolution here which is different from the other, but topologically this is a cone. And this for the tensile force. And then we can extend also these results to the nonlinear case. There are some theorems that help this. So when an invariant cone exists for a piecewise linear system, locally it exists also for a nonlinear, complete nonlinear system. So using I obtained this using the initial nonlinear equation of motion of this structure. And so you can see here that the behavior at the beginning we have the increasing the evolution, the exponential growth of the amplitude here. And this is the final picture, so the analysis of the sort of instability map. So you can have two design parameters, you can leave two design parameters free, and you can obtain the information about the stability, the presence of this instability. So in the red dot you can see that you can find an invariant cone, an unstable invariant cone, while in the blue one you have mu equal to 1, so you cannot say nothing actually. In the part of the graph that is not depicted in yellow, so in the central part, you have both the system are stable. And so you can give to an engineer, to a designer, this map is able to find, to design a structure that is that has this behavior. There are some future research that are possible. I'm a bit late maybe, but I think that one important thing could be try to create a link between these two very different topics in my opinion. So thank you for your attention.
Thank you for your very interesting and surprising presentation and the result, and for as compliment for the tough analytical work that you fight with during this PhD period.
Thank you.
Okay, I have some curiosity about. Let's start from the first part of the presentation. You also actually presented two topics, two different PhD theses as well. You make double work as well. And about this problem, I noticed that you use the pre-stress configuration. You consider the effect of pre-stress.
Yes.
And this typical problem is if you consider a homogeneous starting configuration, you mean when you apply the pre-stress, the starting configuration, the stress and deformation is homogeneous, or the presence of the holes gives you non-homogeneous, complicated?
Well, actually, I did not consider the pre-stress because we decided to neglect this part. So the approximation that I called it approximated cloak because we neglected the part dealing with the pre-stress, so the membrane force and the in-plane pre-stress.
Okay.
So they are very difficult because they are inhomogeneous and the value is very high, and so maybe you can have buckling, and so we decided to see if it's possible to create a real cloak, and so we started to see what happens when we neglect the pre-stress. Is the solution good, or we need to have also the pre-stress to have a good solution of the cloak? And the solution was that it's possible to neglect this part, and we obtain, of course, a bad solution which is not perfect, but it can be considered good.
Okay, thank you. And another point, curiosity, is that you say that you take a coefficient in the stiffness matrix which is very small, the torsion,
Yes.
dxy, xy.
Yes.
Does it give some numerical stability problem because the eigenvalue of the matrix becomes very different, and one of the eigenvalues is actually very small, so you can have some numerical problem.
Yes, not from the eigenvalue point, because this is a transient analysis, so I integrate with a Newmark method the solution. So Actually, they are small, not too small, but they are small. And I didn't find any problem in this case. Because you maybe in the time harmonic analysis could be some problems because you have a sort of defective matrix here, but it's not a problem in a transient analysis.
Okay. About the second part, I'd like to ask you actually if essentially is the non-conservative force, the follower force, which is responsible of this unexpected behavior essentially, and can this result can find application in some practical application in some application, some further application?
Yes, maybe it can be used for energy harvesting, for example. If you use this kind of structure to extract energy from a non-conservative source of energy, you can use this kind of structure, and it could be useful because you give to the designer more freedom, because you can extract energy and flutter also when the system is stable. And also when you have, for example, a weak source of energy, you can use this kind of systems. So there are two stable parts, so that also the energy could be low, but you can obtain flutter in the same way as a system with a greater source of energy.
So you actually exploit the unstable behavior of
yes,
of the not
this is the idea.
Stable, but
yes, the idea is trying to use the unstable.
You are interested in the unstable behavior.
Yes.
So essentially, okay. So I didn't get most of the analytical computation, but how did you solve actually the nonlinear eigenvalue problem? Did you solve it with some approximation numerically?
Yes, with an approximation. So the equation, this equation is transformed into my numerical algorithm into this one. So I have to solve this using Newton-Raphson method. So there are algebraic transcendental actually equation, and so you can solve with Mathematica or MATLAB or something.
Are there some approximation in this approach, or they are solved maybe numerically? Are there any?
They are solved numerically using a Newton-Raphson method. So yes, there is an approximation, but
so they are exact result, but solved, but numerically solved.
Yes.
Okay.
Yes.
And finally, some future development or some further work in progress. Can you speak about some further?
Yes, we can.
Some
As for this part, we can start to understand, to increase the dimension of the problem, maybe because this theory was quite easy to obtain using a two-dimensional problem, but when you increase the number of the unknowns, maybe you cannot obtain this kind of sort of analytical result. And try to find new application, maybe try to find a good application of the instability. I talked about the energy harvesting, but maybe there are other opportunities to other problems that can be solved in this way, and maybe try to find new type of structure that are simpler than this one, because this is not so easy to reproduce in the lab, and so maybe we need to find a structure that is a bit simpler, and we can start in order to appreciate this phenomenon.
So essentially, you have two degrees of freedom. One is the rotation, and the other is the position of
the arc length, the position of this point on the cube.
Can you find some similar behavior also in simpler system with 1 degree of freedom?
In 1D,
or
no.
you need the 2 degree of freedom?
Yes, we need 2 degrees of freedom. Yeah. The initial the initial paper written by the mathematician was a system with 3 degrees of freedom, but we are discussing about general mathematical dynamical systems. So we need to extend this theory to this case, because we need geometry. We need the presence of an invariant cone. So in a one-dimensional system is not possible to obtain. So you have only trivial solutions. Let's say you can have something similar, but not easy to. You cannot see this phenomenon. Actually.
Okay, thank you. I'm satisfied and can leave the question for my colleague.
So also my side, congratulations for your presentation. I enjoyed your presentation, but also reading your thesis this summer. I wanted to start from the first part, but I actually want to ask something about this problem first, because of the answer you gave a minute ago. What is the physical reason why you need at least 2 degrees of freedom? I mean, forget for a moment about the math.
Okay.
So you got a system with a follower force. What is, in your opinion, the reason why you need at least 2 degrees of freedom?
Well, actually, I don't know if there is a physical.
Energetically speaking, let's say, because you developed at some point energetic argument to discuss why maybe the instability is in place from a physical standpoint. So I'm just, telling you, maybe think about the energetics of the system to see whether there is a reason why you need 2 degrees of freedom.
Yes.
Why 1 is not sufficient.
I don't know if there is a reason, because
I'm talking
the
about
non-conservative.
I'm talking about a bar,
Yeah.
some springs, if you want, and a follower force. Right? Restrict the conversation. Let's say.
Yes,
about-
yes. The non-conservative. Actually, in general, you have to consider 2 degrees of freedom when to obtain flutter. This is a general
I know, but why?
situation. Because when you because this it depends on the phenomenon. So you have, it's called Hop bifurcation, and the Hop bifurcation has this behavior. So to have this behavior, this is behavior of flutter, you need in a smooth system, you need 2 degrees of freedom.
I know, yeah.
The reason is, in my opinion, comes from the mathematics, because you define this form of instability, and so.
In my mind, mathematics regarding our activities or my
Yes,
activity
of course, they are linked.
is the language of physics.
Yes,
So
they are absolutely linked. But
I think maybe given a bar with a follower force and a single degree of freedom, do we expect the follower force to perform net work on the system in a cycle?
oh no, it's not possible in that case.
That's the reason.
Yes. Okay.
With 2 degrees of freedom,
You
there
can
is
have
a way to
yes,
extract work
in the cycle. Yeah.
Okay, well, why not continuing with the second part, right? And then maybe ask you something about the first part.
Yes.
So flutter is possible in smooth systems, that is clear, but you have been focusing on this interesting behavior of non-smooth systems, or say piecewise smooth systems. In the specific case you attack, the non-smoothness arises from a jump in the curvature.
Yes.
But what are, say, the sources of non-smoothness that you may consider? Because you said your results are pretty general, so I'm curious whether you could treat the case of non-smoothness arising in the tangent at a point to the profile.
Yes.
Or
In principle, you can describe all kind of smoothness, because the second part, the part dealing with the cone, is general. Of course, maybe your system could present this behavior or not. So, for example, I try to analyze the Ziegler pendulum, some examples, but it's not easy in this case to find with a discontinuous hinge, so the stiffness of the hinge are discontinuous. And it's not easy to find in this case, I have to study more, but in this case it's not easy to find an invariant cone.
But so the theoretical framework is suitable also for, let's say, a V-shaped.
Yes.
And about flutter, a very last question. At the end, answering the questions by my colleague, you mentioned that you may want at some point to extend or say increase the dimension of the problems that you may attack. And I mean, this works made me think about results in the literature about flutter in elastic plastic solids. The guy sitting here is an expert on that subject. So it was possible some time ago to show that in elastic plastic solids, flutter may occur under certain conditions. Okay, but the problem with their analysis is that elastic plastic solids are characterized by a non-linear incremental behavior. Meaning that they may have plastic loading or elastic unloading. So there is, if you want, a jump in the constitutive operator, in the incremental constitutive operator. So all this made me curious, and my question is the following. Do you foresee the possibility of extending all these theoretical tools to attack an infinite dimensional problem?
I think it's
which is still related to flutter.
Actually, when I started to analyze the system, I started from the paper of Davide, dealing with elastic plastic solids and flutter. So I started to thought about this and to think if it's possible to extend this, analyzing better the discontinuity. So the fact that the operator is we have a plastic loading or an elastic unloading. So I think it's possible to study this kind of problem. I have to think about that. I think it's not so easy, but actually you can have the discontinuity could be also in the velocity, for example. It's quite the same. So if you want to design a structure with the discontinuity is not on C but in C dot. Maybe you can do that. So maybe also dealing with the increment is possible. I have to study this. It's not a simple question, but I think it's possible. It's a general framework, so I think it's possible.
That the sources of non-smoothness can be treated both arising from the geometry of the problem or from the constitutive behavior.
Yes, I think it's true. I think that the source of discontinuity is not so important here. Maybe you cannot obtain a result that you want, but the framework deals with a general kind of discontinuity.
I mean, that might be a relevant result because Davide can confirm, and as far as I remember, the results you obtained were obtained by assuming plastic load, right?
Yes.
So
and I started wondering what happens if I have also the elastic unloading, and so I started to study this topic.
I mean, to the first part,
yeah.
Just two quick questions. You wrote your own code, right?
Yes.
And so, how did you implement the boundary conditions? Because I guess the plate is infinite, right?
No, it's not infinite in this case.
It's finite.
And
okay.
It's very large in order to see the transient analysis, in order to see these circular waves.
Taking place at the boundary? I mean,
sorry?
Is there a physical boundary?
Yes, it's a simply supported,
simply
supported homogeneous plate. So
you didn't have to deal with
it's a physical problem, it's not infinite.
And I mean, I got at least in principle how this approach of changing the coordinates may help in attacking problems of this type, but how did you actually optimize the parameters to get a cloak, let's say, a reasonable cloak. Again, did you perform it by, say, hand? Or
Yes.
since you wrote your own code, you also maybe implemented?
The idea of writing a code is also to use a tool to develop also a tool that helps the design of a cloak. So this was the idea.
Yeah, but what I'm asking is, once you have a code,
Yes.
you can use it by, let's say, I change the parameters, I see what happens, and then I choose a solution because I think it's optimal. Or you may include an optimization procedure.
Yes. So here there is not an optimization procedure. This is only an example, but the idea is to introduce this kind of optimization example to.
I guess it would be a very good idea.
Yes.
Since you have your own code, you know every single line.
Yes. The idea of having my code is that I can
Then you know where to
program and find an optimization for this product.
I guess this is on my side. Thank you.
Thank you.
Okay, so just one question. Go please to the very end of your presentation. So the graph on the right.
Yes.
So my question is, so you don't get a unique continuous region
No.
of instability. You obtain many islands.
Yes, it is not possible with this criterion of stability. It's not possible to obtain a classical range in which the analytical range, like in the Ziegler pendulum, in which you have flutter, you have divergence. This is a semi-analytical approach, so you have to test the parameters, and so I studied this discrete number of configurations. So it's not possible analytically to obtain the equation of the area in which you have a solution, an unstable solution. I started to test for each case. So here we have the load, for example, and the ratio of the radii, and you can, yes, there is this shape of the, so you have this part in which you can find the unstable configuration, and in the other part, in the blue part, actually you cannot see nothing because mu is equal to 1, and so in this case you
But
can.
if I enlarge in your thesis, I see some red spot.
Yes, maybe
somewhere.
because there is some, yes, here you can find some isolated point.
So
Yes, maybe the area in which the solution is unstable is very small in this case. In other part is larger, and so you can see
So- you fixed some parameter to
Yes.
get this. So do you believe that by tuning this parameter, you will reach a less defragmented unstable regions?
Yes, I think yes. I'm not sure, obviously you have to find the correct range in which you are interested, but this pattern I think is clear. So
And what do you think it could be the effect of including some viscous dissipation?
the viscous dissipation increases the complexity of the mathematical framework. It's sure.
So sorry. Before that, when you draw, when you highlight with a color the point, you mean that you have solved the existence or non-existence of this cone?
Yes, exactly.
If it exists, if it is attractive.
Yes.
That is the definition.
When I found the red dots are with mu greater than 1, and when I have mu greater than 1, I have always an attractive cone. It is one of the properties that I've shown before. And in the blue part, in the blue dots, you don't know actually what happens. So it could be a stable solution, but it could be also a cone with a greater order, if you want. So you may have more than two So if you perform 2 cycles before, if you start in X and then you go to Psi and then you go to eta and then you start other cycles and then you arrive in the correct eta that is on the straight line, you can have a sort of cone of a greater order. And I'm sure that in some of the points there are also these cases. And so they are complex, much more complex. And they are also, so in this part there are also other parts that could be unstable. This is the problem.
Okay.
So maybe between these 2 patterns there could be this cone of a greater order that are unstable because of this.
So you should confirm with the evolutive problem, I mean, these points eventually or not?
So sorry?
You obtained, you distinguished these 2 behaviors by these cones.
Yes.
So you can also confirm the distinction between these 2 behaviors and maybe refine better some.
Yes, of course you can do refine this area, for example.
No, I'm not saying refining by meshing, but you refine the definition of these 2 stages by considering the solution from the integration of the equation of motion.
Yes. See, yes, the integration of motion. These are actually the result of the integration of motion. So I checked. So
Okay.
when I found each of these points, then I have checked
Yeah, but
integrating the equation of motion.
the unstable points are correct by definition. Because
Yeah.
you have
Oh yes. The other point you have to.
But the other,
yes.
for the blues,
You have to
what does it
check.
mean? The grays point.
The,
Gray points, non-existent.
yes, there are some great points because yes, I gave to the numerical algorithm a grid of points, and so in this part there are some problems.
No, sorry, the
Okay, this
yes,
one.
yes.
Here the algorithm is not able to find a solution, so a cone does not exist in this case. In the blue part, a cone exists, and the multiplier mu is equal to 1. In the gray part, a cone does not exist.
Okay.
The numerical algorithm was not able to find it.
What is the meaning for you? Because is the algorithm or it doesn't exist?
For sure, it's the algorithm. Actually, I don't know.
Because if you integrate the equation of motion, then you will have
Yes, but you have to find the initial condition, the correct initial condition to have a cone. So it's not it's not enough to integrate the equation of motion. You have to know the initial condition. And so here I know the initial condition to produce this graph because I solved the problem of the cone. In this case, I didn't find any cone, and so I should test all the possible initial conditions. It's not possible.
What does mean gamma equal to 0.5?
Gamma is the loading, as you can see here. So it's the ratio between F times L over K2. K2 is the stiffness. So is
A special value of the loading.
Sorry.
It's a special value of the loading.
Yes,
actually.
it's a special value of the load, and is a tensile value.
So sorry, going back to the viscous.
Yes.
The
Okay.
viscous
The
damping,
viscous.
what you
Yeah.
expect that to?
Yeah, it could be. You can see in the energy maybe you have not this exponential growth if you have a dissipation with viscous damping, and so maybe these phenomena could be reduced, so the instability could be reduced due to the presence of damping in general. And as for the physical part, and for the mathematical part, there are some problems because you have more than stiffness matrix and mass metric. You have to consider a damping metric, and this complicates the structure of the equation. Actually, maybe it's not so hard because the matrix exponential is this, and so you have maybe this one times an E over minus.
Can you still define the cone?
In principle, yes, you can define, if you are able to find this, this condition, yes, a cone can be defined. I'm not sure if you are able to find it, but a cone can be defined. You have to rearrange this equation. You multiply this with e to the minus of minus mi t, and maybe something happens also in this case.
Yeah, about the dependence, maybe, I mean, there could be also some paradox. So if you have the viscous damping, you enlarge the region where you have the instability. There could be also this option.
Yes, the zero paradox, analogous to zero paradox, maybe it's possible. In the zero paradox, you can compute analytically, and so it's easy to understand. Here you have only a semi-analytical approach, and so it's not easy to understand.
I'm not criticizing, I'm just saying that since you have a very fragmented regions of instability, maybe by putting some viscous damping
you can
something, you can get a larger domain.
Okay, maybe it's possible.
Just another curiosity on my side. Have you done or? You mentioned off bifurcation.
Yes.
I mean, as far as I remember, off bifurcation requires that a limit cycle is attained, right?
Yes.
Do you find limit cycles in the elastic system?
No, not in the elastic. I found only the cone, and we are actually the limit cycle are in the nonlinear case, and in the nonlinear case, as you can see at the.
So you find
this is a sort of limit cycle. It's not. I was not able to find a limit cycle like a classical of bifurcation, but you can see these nonlinear results. So you have this increasing of the amplitude and then exponential decreasing and changing. Studying, for example, they are in the thesis maybe, studying the case before with tensile forward force and flutter-like and compressing forward force. You can see in one of the two cases, there is a sort of limit cycle in the nonlinear case. It's similar to a limit cycle, not exactly a limit cycle, but you have
you maybe find an orbit, or say a closed curve, within which the orbits are.
Yes, it is exactly. It is not a limit cycle, but
this closed curve is maybe not an orbit. It's not a periodic solution for this system. Because you need viscosity, I think, to meet all the conditions of bifurcation theory.
Yes, maybe.
I think. And this is the case for Ziegler technique, so maybe it's the case also for this.
For this case.
According to your result, you have the instability only for compressive force.
Yes.
Okay, so you cannot find for tensile. There is no instability for tensile.
Can you change the parameters?
You can change exactly. You can change the parameters gamma, and you can obtain this phenomenon both for a positive gamma or a negative gamma. So
in the previous class, when the directed spot only.
He's speaking of the last graph.
Okay.
Yeah.
Yeah, it seems that the red spot are only for negative value of gamma.
Yes, this actually, there are other parameters, so it's not exactly the same parameter before, but here you should find some other point. In the specific case, you should find some red dots also here.
Okay.
So this is actually over the zero, not so much, but is positive, and this one is negative, so there are these highlights.
Okay, thanks. Any more questions? Okay. Thank you again. We need 15-20 minutes to get to fill the forms and everything, and then we can see here in 20 minutes. 15 minutes, ok?
Cioè noi andiamo nell'aula.
Se volete stare qui, la
Allora mi sa che dobbiamo interrompere.
Andiamo nell'aula.
Quindi che avete fatto l'atto pratico? Che risultati abbiamo? Cioè, abbiamo una registrazione complessiva, giusto?
Sì, c'è la registrazione.
Ok, è un'unica registrazione in tutto l'evento.
Poi c'è una registrazione.
Ok, dobbiamo provare però perché non so se c'è un limite di tempo che queste registrazioni devono avere per essere caricate su YouTube. Cioè non so se. Non lo so neanche io. Vabbè, proviamo, vediamo
Anche vado io comunque
No, in realtà
no, quelli lo tagli.
no, dico, in realtà ho comunque la mia.
Ah già,
c'ha tutta la sua, quindi volendo.
Voi state qua, quindi chiudete l'aula, se cioè non lasciate qualcosa con l'aula aperta, se mai chiudete, cioè che state qua, se no vedo che lasciano qua già, se no se voi andate non ce ne sono, perché chiudete la potete dire che è successo. Si possono lasciare aperte con dentro roba.
Ah no? Perché Madonna ti ha fatto venire qua.
No, mi sono letto le frasi.
però ho fatto lo stream Luca.
Sì, l'ho fatto.
Sì, alla fine siamo riusciti, abbiamo solo rifatto
Quello è successo qualcosa.
Ma io penso che sia il primo che sia partire una
Sto pensando che forse perché
Abbiamo fatto la cosa in pratica per capire come mai
no,
quello.
non so cosa sto pensando, perché tu quel link l'avevi preparato senza usare OBS e io quando l'ho voluto far partire l'ho voluto far partire con quello, magari su questa cosa qui c'è cioè anche se è la stessa, magari lui la percepisce
No,
come una cosa
forse
diversa.
non riesce a collegarsi.
No, era collegato.
Ah.
Solo che probabilmente un conto è dire faccio partire il link da browser
lo creo io.
e un conto è lo creo con un software. Probabilmente per YouTube sono due cose diverse, anche se fisicamente, cioè dovrebbe essere lo stesso. Stavo pensando che quella potrebbe essere una spiegazione.
Quindi poi dopo se abbiamo la registrazione di OBS.
Tra l'altro l'unica cosa, non ho parlato se la registrazione l'ho fatta tutta quanta in full HD, cioè quando diciamo, allora, la trasmissione era prenotata, ma la mia registrazione non so se è in 720p. Video? Ah, no. Non ho
Vai pure in bagno.
Oggi filmato.
Vabbè, sto arrivando questo uscire in
Sì, sì.
Come dalle
Però lascialo fuori.
vabbè. Ma sì, perché non so, penso se doveva togliere, però quando li tirati fuori è buono. Perché è stato un peso.
Avete già fatto un
Io se.
No,
Io lavoro in
poi
io
secondo me fa
non ci metto
maybe this, but I'm not super sure. There is white, is yet white, there is only written acknowledgement. So I will decide maybe the day before. No.
Come qua le lasciare le cose più ah sì, qua.
Sì. White, so there is
Sì, ho visto che
lavoro in ospedale, pensi che la croce va avanti molto con la sanità pubblica. Andremo avanti molto con la sanità pubblica, passeremo una segurità almeno perché al nord tutti i genitori dicono questo,
ci sta un cavetto, diciamo.
questo disse ci sia un'emergenza tale per giustificare una cosa del genere, stavo dicendo la guerra, per esempio, la guerra non è che pensasse basta parlare di però io sono colpito perché quelli che vengono così, non è che facciamo politicamente politico se parliamo di live o in treno, non è così, ci vuole un evento particolare. Lo stesso si può fare pensi queste persone che hanno comprato le risorse adesso essere una lezione speculativa non adesso
I choose my favorite, but I didn't read them. How many pages? Now 180.
You want to read those?
I want to read one. No, ora sono noi non possiamo
So you don't have
che stanno succedendo, io l'ho letto,
quel coso,
queste persone che hanno preso l'anno, c'era scritto cose fino a basta, non è che dopo no, tutti seguono bene, in realtà c'è un fatto quindi non facciamo mi piace soltanto no? Che mi sento bene, basta,
the other it was black and white, the non-which
no, questa persona qui però famoso si chiama fa le conferenze sia in Svezia considerato pochissimi questi che giocano
60 euros, I can save it.
Proprio tutto questo transumanesimo, superamento religioni, la mancanza di colori,
Oppure il mio. I don't care.
And there is one color dot. Cioè, convinto di dover guarda in caso, è stato to change a lot of things just to get the one. Also, I found this
I think we did the same format.
template on the internet.
No, I didn't. Allora, let's create only the format. And then for everything, like for the master thesis, for the bachelor thesis, and for the PhD, I write later. So I check more how to a lot of work. He divided each chapter, divided everything, and then link everything in the
A lot of time to just investigate it's very easy. You open up the CMS, there is the A4 where you change it to modify.
Yeah, I know, like, everything changes. I
Okay, now we can send her pictures of the basket. She comes in, she remembers the basket that you had for your birthday 2 years ago. No, you can collect. You can collect. You can. Ma she will be here.
Mi dicono dalla regia che sì. Adesso?
è stata
Because it's 45 minutes, like she's no, rischi di take the car.
Io l'ho vinto con 7 mezzo. No,
non le fasi, tutto quello che abbiamo fatto.
È un ordinato REST, no?
Io prima delle 8
Yeah, right.
Vediamo qualcosa.
No,
Prima ci teniamo il posto, il posto, gli ultimi voi, appena arrivi, poi finisce davanti.
Tanto capisco
because it would be a very flat figure. I know. One presentation. Ah, yes. Thank you. I sent.
hanno chiesto di incontrare dal punto di vista del
comunque
She doesn't know what she
yes,
beginning you need to teach her.
yes. In fact, we use choice when she writes, no, because yes,
That is a nice
because she's so yesterday she positive I saw her
Ci avremmo fatto la città del Luca Organi, questo è un altro direttore del mio dottorato.
Potrei concentrare su questi anni idee. Quello
The one that we
credo che riconoscendo male
Vedi, ma sono io si è visto perché
Non si è visto? Beh, allora mi muovo,
Dobbiamo lavorare su un po' di questo.
dopo a caso la macinata dice che ragazzi
è così.
non è bravo perché tutti questi era da piacere,
Che c'è le
sono contenta che siete stati bene.
però non
Quando volete.
No, perché ci vorrei mettere mano.
cioè vado da così che fai frasi più complicate.
Fa sempre sì. C'era un'unica condizione che valeva per tutti.
Si spacca basso, se io faccio meno quello di spacca, ce n'è una senza Italia che è venuto qua ricordissimo.
Io dovrei discutere prima di Natale, sì, stare un po' di problemi, dovremmo, a breve saprò però, prima di Natale.
Poi dato del deposito
Sì, adesso io sono di Mascalzi, invece adesso sì, adesso io sono
volta risposta.
no, adesso è che mi sto sforzando, non si serve. E poi sto finendo il postdoc sul febbraio e poi dovrei avere il turno, cioè dovrei fare un altro anno.
Perché
Non è un postdoc, ma una simile
quindi posso fare la tesi, poi questa via era tutto fatto
Riccardo fa giù, è rimasto almeno più, anche lui 2 anni ancora.
Questo perché questa rana viene sempre legata al fatto che non riusciamo a controllare.
La vita difficile che dove infatti
poi in realtà pensavo vabbè, dopo una volta che va
Lorenzo è salito
niente, no, però
infatti io sto buon passo, adesso non ci non sono facile
il panno di immagini invece che lasciarla sul c'è
Mi sa di aver capito che mi fermo un attimo sabato. Se non riuscite a riciclare. Ah sì, quando si
Siamo un po' sopati. Però non hai mai visto i video delle facce. Certo, certo. Hai dato finalmente un volto ai nomi. Vabbè, comunque sì, perché pure là io quando vado a c'è Carlo, guarda un ragazzo di Napoli, però poi dopo cioè non associerebbe, no? Immagino che sì, come si trovate?
Infatti nella mia ricerca
tutto bene, sto a casa, lavoravo ai smart work, quindi si trova bene, devo cambiare casa, quella, cioè, non so se era imbarazzante, no nel senso infatti era giornalista che non lei se ne frega, era quella che mi piace, no, sì, no, bisognava lasciarla in due, non si poteva più stare, non c'era.
Avevo fatto una prova,
adesso siamo spostati un po' più sud. No, più lontano, ma cioè,
che speranza c'è
con la macchina, cioè, però a casa c'è un bellissimo terrazzo. Poi la casa non è grandissima, è sempre 45 metri quadri, però cioè, abbiamo di mano, cioè, è un'altra casa. Esatto, no, stai bene, riguarda la televisione, cioè è calda, ma sì, tanto siamo noi due, adesso vado il canino. È cresciuta questa foto, facile questa, si è appena presa. Questa ieri. Sì, ragazzi. Questa ieri. Già è cresciuta tantissimo, io ho detto no ti prego non cresce. Ma questo è un peluche? Quello sì, cioè se lo prende, se lo porta in giro, tu glielo sposti, lei se lo riprende e se lo gli la cuccia. È pazzesco, soltanto che è un po' una bestiolina pazza per giocare, ti morde tutto, però
sai cosa anche il fatto forse il figlio, se uno ha venuto quindi bambino, contatto magari
sì, si ha quasi distrutte. Vabbè, morte per giocare ma molto pesante perché non controlla ancora, no?
Sì, beh, l'avrebbero
sì, assolutamente. È bravissima, c'è un cane estremamente forte. Io non pensavo veramente, cioè mi ha stupito da subito 2 volte mi dice una cosa, lei capisce che dopo le 2 volte tu gli dai il premio, è stata stessa e lei ha capito subito, cioè mi siedo il premio, zampa premio. Però le cose l'ho messo quasi 3. No, perché sono presa. Diciamo che se fossi stata da sola non l'avrei potuto mai prendere. Il fatto che sta a casa e lavora in smart working Fai il marmo, esatto. No, vabbè, però nel senso le abito di uscire, cioè ci vuole aprire la finestra, no? Ma lei là. Sì, lei mangia un po', poi adesso sono un po' di problemi. Allora già c'ha già via, che è un parassitano. La sera la medicina quella c'ha la cistite, mi ha scritto la cistite, quindi insomma ci sia qualcuno. Mi hanno detto che è normale, piccolini sopra le femmine, no, forse la foto, però
molto impegnativo, però veramente la gestione però mi ha dato 11 anni di meccanica, ho lavorato
cioè no, solo non ce la fai,
4 è andata bene,
però adesso con chi è?
la tata,
Ah, ok, in compagnia allora.
Questo è un suo profilo, però vediamo se riesco a trovare guarda, avete
poi posso spiegare qualche animazione grande, grande, sì. Ti salta addosso, no, ti regalano grandi, cioè, sì.
immaginavo me la giornalese.
No, vabbè, corsi, no, anche i corsi in realtà si devono fare. Certo che quando ci facciamo, quando ripariamo gli italiani, però tipo le conferenze, passaggi di anno, gli esami, e poi no, c'erano questi che erano i membri esterni, però non è dell'università, ci vogliono due membri esterni che erano quest'altro signore
di dove era?
non lo so, questo in mezzo a loro due, queste due persone, questo ragazzo e quest'altro signore c'era dal corso che invece è collaboratore con, cioè lavora con Bigoni.
No, non sono commesso.
Il ragazzo, più i due supervisori che non conoscono, diciamo, cioè sono la commissione no, quello che dice
invece
fai bravi, insomma, la canonica, le canoniche sono insomma c'è stato 2 ore sorella.
Sì, ma ora che posso una programmazione non dà niente.
No, il voto non c'è, però dobbiamo magari sempre inglese.
E così è la scusa per non rompere qualche volta. Bene, vuoi parlare in italiano di investimento?
Sì, sì.
Bene, allora oggi siamo giunti a un percorso di 3 anni, un lungo percorso difficile, complicato, intenso e faticoso soprattutto, che è stato 3 anni fa e che ha portato a una crescita non solo di età ma anche di spessore dei candidati e praticamente aumenta sicuramente il loro livello di professionalità che sarà poi utile nei prossimi anni a venire per la loro carriera che auguriamo sia fruttuosa. Quindi ringraziamo essenzialmente i candidati, i tutor che hanno praticamente favorito e permesso insomma, la conclusione delle tesi di dottorato e i commissari che sono intervenuti a questa cerimonia. E procediamo con la proclamazione dei candidati che naturalmente hanno conseguito il titolo di dottorato e adesso uno per uno in ordine alfabetico praticamente pronuncerò la formula di proclamazione di dottore di ricerca in inglese perché così richiede la procedura. Allora, il candidato Riccardo Cavuoto, on the behalf of the Honorable Rector of the University of Trento and on the basis of unanimous judgment of the final examination commitment, of which I am the President, I declare Riccardo Cavuoto Research Doctor in Civil, Environmental and Mechanical Engineering. Best congratulations. Next candidate is Dr. Marco Rossi. On behalf of the Honorable Rector of the University of Trento and on the basis of unanimous judgment on the final examination commitment, of which I am the President, I declare Marco Rossi Research Doctor in Civil, Environmental and Mechanical Engineering. Best congratulations. Ok, thank you, grazie a tutti i partecipanti, auguriamo una carriera, come dicevo prima, fruttuosa, lunga e divertente anche ai candidati, perché c'è anche un po' di divertimento in questo lavoro, insomma, non è solo fatica. Non ci vedo. Ma tanto tutto registrato, annullato il titolo di tutta di ricerca. Chiudi te o Luca? Sono poi chiari.
Chiamare concluso da passerella.
Gli ultimi mesi, gli ultimi giorni, questi giorni del dottorato mi ricordo una fatica bestiale, insomma. Il tempo che non mi bastava mai il tempo, giorno e notte. L'ultima notte penso che non ho neanche dormito, insomma, prima del dottorato per finire, non c'era ancora i processi, si faceva tutto con la macchina da scrivere, insomma, ma adesso mi vedo qua, insomma, alla fine tutto finali sono tornati adesso queste qua sono le cioè quindi Adesso lo chiameremo anche noi,
Sì, ma io faccio
Vediamo magari calma, sì, ma
Ciao ragazzi, ciao. Parla.
Questi due fenomeni praticamente organizzano le cose e dicono no, noi non vogliamo parlare col pubblico caro, no? Ma che cazzo.
Ciao a tutti.
Ciao, io ho chiuso l'orario.
Dimmi tu ora, Matteo, domani.
Andiamo a provare io domani sono
11 e mezza, che ora 12 e mezza.
No.
Ci vediamo alla mezz'ora allora. Io vengo e mi iscrivo.
L'ingresso?
Perfetto. No.
Io del pesce, questo li davo per scontato. Smetti di scappare.
Grazie.
Adesso se loro fanno tutto così, quello abbiamo mangiato ieri, poi la nostra volta continuata. Andiamo nonlocal, mi piace da morire. Sì, viene anche la mia ragazza così lo faccio trovare. Dai, la gnoccata è andata allora.
Mi piace. Siccome è il ristorante preferito del mio...
Grazie.
la prestazione è anche ottima.
Mettiamoci a impossibile. Sono frequenti, lo devi quando il pacchetto complesso.
Chiudiamo? Sì, vai.
Hai saputo come dire.